having that clock there is great, because I do not need to look at my computer or anything else to know if I'm on time. Every conference should have a clock viewable by the speaker. Yeah, very useful.
Okay, I think we are more or less ready to start. If you guys would come in and settle. Okay, so we are returning to the topic of extreme star formation, and right now we have Ben who's gonna talk to us about starburst.
Great, thank you, Maya. Cool, so yeah, my talk today is really going to be talking primarily about the phenomena of starbursting, whether starbursts as a kind of galaxy or starbursting as a thing that galaxies do. And related to that question is, just because something is extreme, does that mean it's rare? And I know that a little bit this is kind of a definitions question, which can be a little bit boring and a little bit unstimulating intellectually, but I think that there's something to this. So let's start out now by talking really about the observational context, because ultimately we're empiricists, we're scientists, we want to know what really happens in nature. So starburst galaxies have been known for a long time. They were first discovered and identified as kind of irregular, dust-obscured galaxies with relatively high star formation rates. So kind of the classic example here is the Antenna Galaxy, this merger that's very dusty, so you can see these dust lanes, and also very blue and red, which you can see as star formation. One of the features that really categorizes starbursts versus sort of more normal star-forming galaxies is their very short depletion times. So even normal galaxies typically have depletion times shorter than a Hubble time. Starbursts have depletion times significantly shorter than a Hubble time. And our understanding of them really began exploding in the 1980s with the first launch of infrared space observatories. So IRAS identified something in the 80s that today we're very comfortable with, but really as a new kind of galaxy in the sort of long history of astronomy. LIRGs and ULIRGs. These are luminous infrared galaxies or ultra-luminous infrared galaxies. These are starbursts that are so dust obscured that the majority of the luminosity coming off of these things is actually coming off in the infrared, in the far IR. And with ALMA coming online in the 2010s, we've now identified also high redshift analogs of these LIRGs, submillimeter galaxies. So if we look at sort of where they lie in typical galaxy scaling relations, starbursts lie above the kind of main sequence of normal galaxies. They're about 10 times higher in star formation rate than you would expect based on just their stellar mass. And if you look at this in surface density, like the Kennicutt-Schmidt relation, they lie up here where you have depletion times of around 100 megayears or so compared to the sort of normal disk sequence where your depletion time's about a gig a year. They're also very dusty and very rich in gas. So if you look at how much molecular gas is within these things, strong starbursts are significantly above the sort of main sequence of star-forming galaxies, and extremely dusty compared to the main sequence of normal galaxies. And they also tend to be quite compact. So the question I kind of really want to focus on today is this a thing that happens to galaxies, or is this a thing that galaxies do? Is this a mode of star formation, or is it something that happens to a galaxy and that makes a galaxy a starburst? So let's start by comparing what we're talking about with burst mode versus equilibrium star formation. So if your depletion time here for your gas is 100 megayears or so, you know that you can't be in a steady state without some new fuel coming in. You will exhaust your fuel in 100 megayears, which if you think about the Milky Way having a dynamical time of 250 or so megayears, these things are going to exhaust their gas in less time than it takes them to complete one rotation. And it turns out that generally we think that they're deplenishing this gas faster than it can be replenished through accretion. So this tends to bring us sort of to this conclusion that this period, this mode of bursting must end. Either it ends by exhausting the gas, it's used it all up, by blowing that gas out, so through some sort of large galactic fountain or outflow, or maybe somehow by just lowering the star formation rate and returning to equilibrium there. So I want to start us out in the theory side of things, working with some analytic models for how you can estimate and predict what the star formation rate in a galaxy is going to be. And probably the easiest one to think about and work with is the so-called bathtub or gas regulator model. This is something that's been developed over the last 20 years or so, and it's a really simple set, really it's just one differential equation here, that's thinking of galaxies as essentially a bathtub. You have stuff flowing in, gas inflowing into the galaxy, and stuff flowing out, either from outflows or by removing that gas, turning it into stars. And so you end up with this simple differential equation here saying that your rate of change of gas within the galaxy is the amount of stuff that's inflowing minus a couple of terms relative to the star formation rate. So these terms that are related to the star formation rate, the first one should be easy to understand. So minus 1 times m star is just the star formation rate. So you are removing mass in gas by turning it into stars. But then we have something here with eta, which is our outflow rate. So that, if we go back, is the amount of material that's being kicked out of the galaxy relative to how many stars are formed. And you're probably kind of curious about the fact that we've got a negative sign here in front of this final third term. This is gas that's being returned to the ISM. So we know that stars, even if they don't necessarily die as supernova, will die in one shape or another. And in that process, either by exploding as supernova or blowing their outer shells out, will return material to the ISM. So if you make one simple little assumption here that you have a relatively constant or at least slowly varying gas reservoir, you can just calculate what the star formation rate of a galaxy is based on its inflow rate and these two parameters that you can wave your hands about with theory to try and understand and get this gas inflow rate from whatever semi-analytic or simulation model you want. And this works pretty well. This is pretty good at predicting things like the star-forming main sequence, but it lies on this one assumption that your gas reservoir is relatively constant. And if your depletion times are super short, you can't make this assumption. This assumption is broken. So the bathtub model has to be modified in some way if we want to use this simple analytic approach to understand star formation in starbursts. And one of the ways you can do this is by basically taking into account the delay between star formation and feedback. This ends up giving you an oscillator type model. So here you can see one of these oscillator ODEs integrated over time where you have bursty star formation at high redshift, eventually settling onto kind of an equilibrium mode. And the picture here, I think this kind of schematic from one of Phil Hopkins' recent papers is really easy to understand. So in a shallow potential well where you have bursty star formation, you need to balance the pressure to keep your ISM by the pressure that's injected by feedback. Well, if the escape pressure is low, in other words, if the escape velocity is low, when you form stars, you blow most of your ISM out, it recycles, and you end up having this oscillatory behavior in star formation. Meanwhile, in a deep potential, it's very difficult to have the entire galaxy form enough stars at once to blow your entire ISM out. So effectively what happens is all of star formation is bursty. It's just no longer correlated in space and time. Little bursts throughout the disk will form your clusters and associations, but because you have enough of those little patches that are forming stars at different times with phase offsets in their timing, this all integrates to kind of a smooth star formation rate overall. So just to get us started on kind of an analytic understanding and the observational context, when I'm talking about starbursting galaxies, I'm talking about galaxies with short depletion times. Observationally, we see that they often have irregular morphologies, but not always. They often, almost always, have high gas and dust fractions. They're often more compact, and they're very, very common at high redshift. So I want to do a little bit of quick group discussion here. Let's think about these questions. Just throw up your hand when you have an idea about one of these questions, and I'll write them on the board, and we can kind of collect our thoughts before we move on to the next part.
Galaxy mergers can trigger starbursts.
Ooh, good idea. Mergers trigger starburst. Cool.
Maybe not a merger, but like a close passage, so you get some kind of density disturbance that travels through the disk, and maybe a shock front triggers a starburst in that way.
I'll call that tidal perturbation. And excellent. Absolutely. Maybe you don't need to actually slam things together. You can just throw them past each other.
Starbursts could alter galaxies by depleting all the gas and turning them into like what's it called? The galaxies that have no gas in them.
Yeah, it turns a late type galaxy into an early type. So I'm going to write that as starburst kill. Because that's fun.
Another quenching mechanisms could be like maybe being a satellite, being a small mass and getting your gas ripped off.
Okay, yeah, maybe you could kill a galaxy off without actually triggering a starburst, just by like harassment or ram pressure stripping. Okay. Yeah.
About triggering also can be positive feedback from AGN.
Oh, good idea. Good idea. Positive AGN feedback.
It might be part of the perturbation, but it could also be gravitational instability.
Ah, so maybe you don't necessarily need an interaction. If your disk is unstable by itself, you can build up big clumps. That's a great one. So I'll just call that gravitational instability.
About how rare are starbucks, I would like to add which cosmic time,
Ah, yeah, yeah.
because at redshift 2 cosmic noon, they are expected to be the most common objects in the universe.
Exactly. Exactly. So when you ask yourself, are they common or rare, that answer might be different if you're at a different time. Anything else? Any ideas about this last one? Like, besides changing the star formation rate, are there any other ways in which you can transform a galaxy? Like, you could maybe you turn it from late type into an early type. Anything else you could do? Okay, cool. Well, I'll tell you about some other things you can do later on. You haven't stolen my thunder. Cool. So this is actually pretty comprehensive. Like, you guys already understand starbursts pretty well, especially in the observational context. Like, it's totally true that starbursts are ubiquitous around redshift 2. And this idea, for example, that mergers or tidal perturbations trigger starbursts has really for the long time been like the simplest, most logical explanation for understanding starbursts. So I'm going to talk about some of these ideas and dig into more detail. So let's start now by talking about mechanisms of triggering starbursts. So I'm going to shift now because I have a bias. I'm a simulator. So much of what I'm going to talk about for the rest of this talk is the results from simulations, because I can actually just throw two galaxies together and see what happens in a simulation without having to luck upon them in observation. So let's talk about mergers to start. So we've been throwing galaxies together to see what happens during mergers, quite honestly, since the first numerical simulations ran on computers. One of the very earliest simulations that most people who do simulations are always in awe of is Toomray and Toomray 77. It's 77? Yeah, I think it's 77. Where they were trying to understand the tidal morphology of the antenna galaxy. This is like really back in the heroic age of using computers, like punch card simulations. But now we have more sophisticated simulations. We have gas, we have star formation, we have feedback. And generally, pretty much all of the simulations agree. If you have a major merger of two gas-rich galaxies, you are going to induce a burst in star formation. And you're not just going to induce it when they finally coalesce, you're going to trigger a burst during this tidal perturbation period. So on the first passage here, shown in red, you actually can trigger a burst in star formation. But you have to be careful in interpreting simulations. And now I'm going to shit all over my entire field. Because you observers are lucky. You get to see what nature does. Now, you of course, your life isn't easy. I'm not saying it's a walk in the park. You have to deal with resolution, instrumental effects, things like that. But all of those ultimately just obscure what nature is doing. We, as simulators, however, are not doing what nature is doing. We're running an analog of nature where the resolution limit imposes a restriction in terms of what the physics can ultimately do. We hope desperately, oftentimes late at night at 3 a.m. staring at the ceiling, that we manage to deal with this resolution effect, but it can change the answers sometimes in your simulations. And one of the places this can happen is in terms of how your star formation models behave. So here you can see a simulation of two mergers, or of two galaxies being thrown together in a merger, run at two different resolutions. And because at lower resolution, that artificial support from your lack of being able to resolve small dense things makes the star formation less bursty, you end up getting a order of magnitude lower burst in star formation at that first pericentric pass. So you might, if you only had access to kind of low res for 2011 simulations, might underestimate the influence of mergers on triggering starbursts. But that doesn't mean that we should give up on this. It means that we have to understand it and we have to kind of quantify these uncertainties. And we can start using these things to like in both cases, you do see a burst in star formation. So qualitatively, at least, I wouldn't throw the baby out with the bathwater yet. One of the things that's great that we can use simulations to do is test different assumptions about the underlying physics, because unlike in a real galaxy, I can't go out there and flick God's nose and tell him to turn off a piece of physics. I can do that in my simulations, though. And so one of the places this is really important is in this idea of gravitational instability. So about 10 years ago, there was this really huge burst of activity associated with observations of high redshift. Now, at the time, this is like redshift 3 or 4 galaxies with clumpy morphologies. These were starbursting galaxies where most of this star formation was happening in these large, massive clumps. And the question was arising, how do you get these clumps? So the first thing you would think of is, of course, tomb ray instabilities. If your disk is tomb ray unstable, it's going to fragment. And a lot of early simulations were finding that it's very easy to build a tomb ray unstable disk that fragments into these little starbursting clumps. But it turns out that this is very sensitive to the feedback model that you use. So this is a paper I worked on with Lucio that was seeming to suggest that these clumps are not necessarily as easy to make as you might think. And one of the reasons why is that feedback can destroy them. A second is that this violent disk instability may not be as violent or as common as we might think, that different mechanisms may actually stabilize the disk, including that feedback itself. So we do think that these gravitational instabilities may also be another piece of the puzzle. And the cool thing about this is all you need to trigger a starburst through a violent disk instability is a sufficiently gas-rich disk, because then it becomes tomb ray unstable. You don't necessarily need to have a merger or a tidal perturbation here. And one of the things that I think is most important that we've written down here is that these aren't rare. If you're talking about the high redshift universe, if you look at any simulation, for example, or look at the observations around redshift 2, mergers are frequent and violent. And so simulations I've run or simulations from the FIRE group, it's very common to find galaxies that near redshift 0 have nice, steady, smooth star formation rates going through a long period of bursty star formation until they eventually settle down. Meanwhile, and this is important, we'll get to it in a moment, smaller galaxies seem to have bursty star formation throughout their entire lifetime. So I didn't see this as a thing that got mentioned here, but one thing that's related to this idea that starbursts can transform disks into ellipticals or late types into early type galaxies is that we're starting to see that this may not be as simple as we had initially thought. So if you go again to analytic theory and look at the stability criterion for thin disks are very, very, very fragile. It is trivially easy to heat a thin disk and turn it into a thick one if that disk is collisional or collisionless. However, as soon as you include gas, it's very easy to actually regenerate a disk. In fact, Floor has a very cool paper from the last couple of years with a thin disk forming at redshift 4 that certainly if we ran it to redshift 0 would get destroyed and reformed over and over again. So you can see here in collisionless models, it's very easy to take an initially thin disk and puff it up. And once you've done that, you're kind of doomed. However, if you include gas, because gas can cool, it can shed some of that random motions through shocks that then radiate energy away. it's actually easy to rebuild disks. So starbursts may kill some disks. They may turn some late type galaxies into early types, but it may not be a one-way street. In some cases, in fact, most likely for these high redshift cases where every galaxy goes through periods of many starbursts, if every starburst destroyed a disk and rendered your nice little star-forming late type into a red and dead early type, there would be no star-forming disks in the present, because Milky Way's been through a period of burstiness. All of the galaxies that we see have been through periods of burstiness. So takeaways from here, I want you to think about mergers bringing in gas and torque as the way that they trigger starbursts. So you can torque a disk to move gas to the center where its surface density will increase and its star formation rate will go up. Or you can just throw a galaxy into another galaxy and, well, it brings the gas it had along with it. So you need to take your nice equilibrium, disrupt it some way, either through a gravitational instability or some sort of perturbation or merger. The low mass and gas-rich disks that we see at high redshift are probably susceptible to a violent disk instability. How much that violent instability actually triggers big clumps, we don't really know very well yet. And finally, don't think that just because something had a big starburst in its past that it's a one-way street to transform disks into ellipticals. Okay, so I want to talk now about this idea. Not necessarily positive feedback, but feedback in particular. The last question that was on our initial group discussion there, namely, what can starbursts do to galaxies to alter them? And the thing that they do primarily, and that I consider to be the most important thing, is that they drive winds, super winds, out of the galaxy. It's the reason my whole background slide this whole time has been M82. Oh, it's Chekhov's M82. You can see this is a starbursting dwarf galaxy driving a massive H-alpha outflow out of it. And galactic winds and outflows are not something that we think might be triggered by starbursts because, oh, maybe the simulations need them to get the answers right. They're ubiquitous. We observe galactic winds in effectively every starburst we can look at where we've observed deeply enough. And in fact, started my PhD, one of the most common ideas for trying to understand where where winds and outflows happened in galaxies was this idea driven by observations of starbursts called the Heckman limit. In sort of early 2000s era observations, it was seen that every galaxy with star formation, well, not necessarily every, but the vast majority of galaxies with star formation surface densities above 0.1 solar masses per year per kiloparsec squared had outflows in them. So if you go down here and look at an observation from this era, you can see that sort of right around 0.1 solar masses per year per kiloparsec squared, you have ubiquitous detections of outflows. Below that, no detections of outflows. So at that point, it was kind of thought, oh, you don't get outflows unless you have a starburst. Now, it may be more complicated than that, but it's definitely true that starbursts drive big outflows. And one of the ways that they may drive big outflows is actually unrelated altogether to the star formation itself. So it is very, very common to find AGN activity concomitant with starburst activity. So ULIRGs and submillimeter galaxies very, very often show evidence of AGN activity. Sometimes it's big and obvious, jets and outflows that way. Other times it's more subtle in the ionization state of the ISM. But the same thing, the same physical process that we think of as driving starburst events in terms of the star formation rate, namely more gas, and gas that's torqued to push it towards the center, obviously must be connected to AGN fueling as well, because what do AGN eat? Gas. Where do they eat it? You can see that when you have a burst in star formation, right here in the yellow, you see a uptick, almost a step function in the stellar mass. A few moments later, which, I mean a few moments in cosmic time later, the mass of the black hole also rockets up, because that same fuel that has driven the starburst activity has also driven AGN fueling, which then triggers AGN feedback. Now, whether or not this actually acts as a positive or negative feedback is a whole other talk. Yep?
Organizer from IISC. Sorry, if I may ask a question as a tutor.
Absolutely.
Well, I'm not a tutor. So my favorite question is always, because I always hear like AGN, 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 drive outflows and regulate. So what is the ratio of gas that gets ejected from starbursts versus AGN?
Oh, that's a great question. It'd be wonderful if someone was working on a simulation project.
Because I mean, I
to
see in
ask
the
that
Galactic
question.
Center we have almost, or we had a starburst maybe a while ago, and it's not clear whether there was strong AGN activity. Probably there was a bit, but we still have a huge outflow, and in principle, star formation can do a lot of that. And I don't know. I mean, the mass loading is probably more important from the star formation, because it's a much bigger area of the galaxy, in my opinion.
I agree.
People always only talk about the black holes because they love black hole. They're cool, but then star formation is not as cool as a black hole.
Well, I think star formation is as cool as black holes. And yeah, you're totally right. It is effectively impossible to, just by looking at a thing, disentangle whether or not outflowing material was put into that outflow by an AGN or a starburst, except in like the most extreme cases. Like, we don't think that stellar feedback can drive winds that look like relativistic jets. But if you just see a wind, a fast, maybe couple 100 kilometer per second wind coming out of a galaxy that is both starbursting and having a bright AGN at its center, I don't know how you would disentangle those things observationally. However, I do know how you might start to look at this in simulations, and you just do two simulations, or two sets of simulations, one without AGN feedback and one with. And from those two, you can basically look at the difference in the outflow mass loadings between the two, one with AGN feedback on, one without. Now, that does not answer the question completely, because of course these things are coupled, and there are non-linear ways in which the two things feed back. Without AGN feedback, you probably have a stronger starburst. AGN feedback, you're going to suppress the star formation, and so it's non-trivial, but one of the things that, like I said, I'm working on here is a big suite of simulations with different knobs turned on and off, so that we can at least start to get a reasonable idea about this as a population. The one place I do think AGN feedback has to be critical, though, is in galaxies more massive than the Milky Way. It's a very, very common, I think, uncontroversial result that simulations without AGN feedback build galaxies above L-star that are way too massive in their stellar population and way too centrally concentrated.
Maybe to add something to the discussion, if may I, and a little bit
Absolutely.
of self-promotion.
Excellent, the best kind.
We have a few months released a paper on Juliers, and we observed in some group of Juliers, a really low percentage of them, that they don't show clear emission features of AGNs. The pH is still really strong, and there is no neon 5, little oxygen 4. And basically, we observed that they undergo an inflow process, and outflows from with a stellar origin can retake them into the self-regulated state without the AGN playing a major role. So they are close to the limit of what you have said now, which was the part I was expecting, like the stellar mass, because it's really important. It's at the end is the major role, because you need to regulate that.
Exactly.
But in that limit, close to that limit, we can still see that maybe there is a little bit of AGN feedback for sure, because accretion can go all along the disk. But from a stellar feedback, it's possible.
Yeah.
So I agree with you. Are fancy, but there is components.
Okay, any other questions before we tick back? Excellent. Oh, good. I was worried I'd just be talking here for an hour.
I wanted to add a comment about so what drives more gas outside of galaxy AGN or starburst
Yeah.
outflows. And I think the wind speed of starburst are not fast enough to bring it beyond the virial radius. You know, it doesn't bring the gas too far, so that gas will eventually go back, while AGNs are more powerful in driving the gas, the baryonic matter outside, so that gas will go into the IgM essentially, or something like that. I don't know if it's wrong, but
Strongly agree. It's right. No, it's right. You're right. If you look at this, and again, simulations are not reality, but this is an AGN-driven outflow that's purely driven by thermal effects, and you're getting velocities in here of thousands of kilometers per second. Now, that being said, the escape velocity for the Milky Way is 200 kilometers per second. For a little dwarf, it's much lower. So in smaller systems, stellar feedback alone can actually drive material out beyond the virial radius. And I'm going to argue in a moment that anyone else have any other questions? Okay, all right. So I want to just leave this with a big question mark. So ignore AGN for now because this is a star formation conference. And I want to talk now about these outflows, how they move, because what Angela mentioned here, is critical. What do? Because if your outflow is a little poot of gas that falls back in a megayear, it's not really going to regulate star formation. So there's a couple of analytic approaches besides just simulating things and watching where the gas goes that we can use to understand this. So I'm going to talk about three here, three different analytic models for understanding these winds. And the first one, it's a really cool paper. I love papers like this where Locas here, she took results from the 70s. Stuff that, like, again, back in the day when you could smoke in the classroom. Like, you'd think it would be too old to be useful, but no, these things physics is physics. And if you're familiar with stellar winds, you're familiar with the Weaver solution. So this is a shell that's driven by a mechanical luminosity. So what Locas did was adapt this, where instead of saying I have a stellar wind with a certain mechanical luminosity, I have an entire galaxy with a mechanical luminosity, and that mechanical luminosity is just my star formation rate multiplied by the amount of energy per supernova I get. So this gives you a certain luminosity and energy per time. And if you plug that back into the Weaver solution, you can get a radius for the inner edge of this hot shell that depends on your star formation rate, the average density of your CGM here, and time. And you could just run this forward. And one of the things that I think is really insightful, 1D models, we talked about this earlier, 1D models are wrong because the galaxy, the universe is not 1D, but they're good insight pumps. And one of the things this insight pump can tell you is that if you form the same amount of stars, so you're forming here a couple billion solar masses worth of stars, either in a 1 solar mass per year interval, a 10 solar mass per year interval, or a 100 solar mass per year interval. So these vertical lines here shows when the star formation event is done. You've formed the same amount of stars. So the same amount of energy has been deposited as supernova. But the radius of this shell at the contact discontinuity here, in the case of your slow and steady star formation rate, never gets further than about 10 kiloparsecs. So nowhere near, this is in a Milky Way-like halo. Milky Way's virial radius is about 250 kiloparsec. So this thing barely gets one disk scale length up before falling back in. If you increase the star formation rate by an order of magnitude, you can actually punch past the virial radius. These are different colored curves for different assumptions about the cooling rate. So maybe if you have the most aggressive and generous cooling rate assumption, you can get out past the virial radius. But if you increase by 2 orders of magnitude, so you're really deep into the starburst regime here, even though you've formed the same amount of stars, deposited the same amount of energy into the same system, you end up basically always, no matter what your assumptions about cooling are, driving a wind that gets out beyond the virial radius before falling back in. And whether or not it falls back in is kind of a question about mixing in the IGM, etc. So supernova are one way of driving these winds, and if you think about what we talked about observationally at the beginning here, that starburst galaxies are very dusty, what do you think of in terms of light when you think of dust? Candy time. Reddening? Reddening? What's even more extreme than reddening? Oh, I heard something that start with an EX. Extinction. Extinction. So what's happening physically with extinction? Photons are either being absorbed or scattered by dust grains. And let's go back to like modern physics 1 in your second year of undergrad. What do photons carry with them besides just energy? Momentum. Momentum. Exactly. So if you're a dust grain and you're getting hit with enough photons, momentum conservation means that you're experiencing a radiation pressure. This is radiation pressure. And so dusty starbursting galaxies may actually be able to drive winds and outflows, not driven by supernova explosions, but actually driven by the light of those new OB stars. So this is a very fun, cool paper Norm Murray worked on about 13 years ago, where he looked at the radiation pressure, which is just a force that's your luminosity divided by C, and you plug that into some analytic models of gas disks that are dusty so that they have an optical depth of around 1. You can show that in a case like M82, where you construct a disk that has about the same size and surface density as the gas disk in M82, radiation alone from clusters, basically any cluster bigger than 1 million solar masses or so, can actually drive a radiation-powered outflow at a couple hundred kilometers per second, which is higher than the escape velocity for that galaxy. Meanwhile, if you compare that to something that's not a dusty starburst, like the Milky Way here, you effectively have to get up to around 3 million solar mass clusters. Really, you have to get around 10 million solar masses before you can approach the Milky Way's escape velocity. And even then, because this shell thins out and its opacity drops, these outflows will probably fall back in before they reach the virial radius. And for those of you who work on clusters, I'm right in saying that the Milky Way is not forming any 10 million solar mass clusters right now. Is that right? About right? Maybe? Maybe a couple? Probably not that many, I hope. So this might be an important mechanism for driving winds in very, very dusty systems, and especially very compact systems like M82. And I would be remiss without self-promotion. I have my own little 1D model for driving outflows and winds, and it's essentially a model that works on patches of the ISM, rather than treating the whole thing as one big spherically symmetric disk. We can use the fact that feedback generates heat, which generates entropy, and the way in which convection works, namely, if you have more entropy than your neighbors, you're going to move up. That's how convection works. So this feedback heated gas may actually move out, away from the galaxy, not because it's given an initial kick of 1,000 kilometers per second or so, but simply because it's buoyant relative to its neighboring CGM. So you can write out the equation of motion for a little buoyant blob that's going to depend on the entropy generated by your super bubble, the virial entropy, which you can get from the virial temperature and the density of gas within the halo, your virial radius. This alpha here is the slope of the entropy profile, which you can measure observationally, and then 2 bits of physics that we understand pretty well, gravity and drag. And the interesting thing about this that's very different than those other 2 models I talked about is you never reach high velocities. So if you look at the velocity of the outflow here, you start at around 150, 200 kilometers per second, which is well below the escape velocity of the Milky Way. And despite that, for pretty much all halo masses around the mass of the Milky Way, it's going to take you a couple billion years to reaccrete because that buoyancy slowly lifts you up and then you fall down. Because you're being accelerated the whole time you're rising, you don't need an initial high velocity. So this may also be important for driving these starburst-driven winds when you don't necessarily have one global shell being driven out by feedback. So I want to go back again to, I know I said leave this with a question mark, but the AGN question. Because we do find that starbursts are ubiquitous at high redshift. So if you look and zoom into the star formation rate between redshift 6 and redshift 5 for a simulation of a Milky Way, if you smooth it on very small timescales, you've got big bursts going on over time. If you look at similarly correlating that star formation rate to the outflow rate, you get big bursts, again before redshift 2, this is a thing that ends up like the Milky Way, that a few moments after your burst you get a triggered, or not really a triggered, but a causally linked burst of outflow activity. The fact that this shuts down eventually is really important, and it may actually be important in triggering AGN feedback. Because if you are removing material from the disk, you're not just removing these outflows from the central region of the galaxy. If you are having a starburst galaxy throughout the disk, there is gas being removed all the way through the disk. And so if the material that's going to fuel your AGN has to travel through the disk, get torqued and lose its angular momentum until it eventually falls into the center, well, every parcel of that gas that you kick out instead is a parcel of gas that's not going to fall into that central AGN. So one of the things that we're starting to see in simulations like FIRE and some of my own is that there is a correlation between the efficiency of stellar feedback driving outflows in this bursty mode and the turning on of an AGN. It seems to be, and again, this is somewhat tentative, but it seems to be the case that one of the ways in which AGN turn on is when the galaxy reaches a point where this starburst can no longer drive a massive outflow, and the torques that have oftentimes triggered these starbursts now start funneling material into the AGN, and you kind of hand off from a galaxy where you are regulating the formation by stellar feedback to one regulating that formation by AGN feedback. Yep.
Does the timing between when the burst occurs and the AGN outflow starts tell you anything interesting about the physics going on, like the timescales between them?
Ooh, probably a lot actually, but I haven't really looked into that question myself. There's definitely a ton of physics involved in the timing between starbursts and stellar feedback driven outflows. So this tells you a lot about like how quickly do outflows propagate through the CGM. Things like mass loadings, I should have mentioned. This eta here is the mass loading of a wind, and you can see in a more massive system that mass loading craters around redshift 2. So most likely this would be around where an AGN would turn on and take over. Yeah. Okay, so there's one last thing I want to talk about with outflows, and it's the hardest one, because it's the one that we understand the most poorly. It's the fact that outflows are multi-phase. We see in observations of starbursting galaxies where we can detect outflows, we detect outflowing material, when we're lucky, in soft X-rays. That's that hot supernova heated gas. We also detect atomic gas. We also detect molecular gas. We also even detect dust quite frequently. And that might not seem strange because, of course, this is ISM material that's being kicked out. The problem, though, is if you ask yourself, how long does it take a cloud in a wind to get crushed and mixed through Kelvin-Helmholtz instabilities? That cloud crushing timescale is set by just a few small parameters. The radius of a cloud, again, we're assuming a spherical cloud here, the velocity of that hot wind, and the ratio of their densities to the 1/2 power. So this is effectively the timescale for Kelvin-Helmholtz instabilities. To mix a cloud, think of a cold molecular neutral cloud being carried along by a hot wind, you can figure out how long it'll take to mix in with this equation. Now, modulo, of course, the fact that they're not a bunch of little bowling balls. And if you ask yourself, okay, if the molecular, dusty, dense, neutral components of my outflows are being carried along by hot gas, supernova ejecta, AGN heated outflows, etc., they begin at rest relative to the ISM, and that gas impinging upon them through ram pressure accelerates them, carries them out in the wind. And you can calculate analytically how long that should take as well. So the acceleration time, the time it takes ram pressure to get a cloud up to move about as fast as that wind, is also just a function of the cloud radius, the ratio of the cloud density to the hot wind density, and the velocity of the hot wind. And you can rewrite this in terms of the cloud crushing time, and at this point you should be panicking. Because is this positive or negative, or is this ratio here going to be greater or less than 1? Is the density of cold gas going to be higher or lower than the density of hot ejecta or hot winds? Lower. Give that man a candy. Yeah. So this cold gas should be higher density than this hot gas. So the fact that this is going to be greater than 1 means that the time it takes to accelerate a cloud is always going to be longer than the time it takes to crush a cloud. So if it takes you less time to mix a cloud into a hot wind than it takes you to accelerate a cloud into a hot wind, why do we see any cold clouds in hot ejecta? Outflows should purely be single hot phase material. And this is really one of the most active areas of exploration in this, because this has tremendous implications for the content of the CGM, the cooling times within the CGM, and most likely what it's going to be, what the answer here is going to be, is complicated. Because we've tried a lot of things, and some of them work and some of them don't. One of the ideas that seems to be very, very promising here is that when you drive a massive multi-phase outflow from a gas disk, this is some of the simulation work done by Evan Schneider with her Choya code. Makes me jealous every time you know those papers you wish you had written? Choya is a code I wish I had written. But this is a really, really efficient GPU accelerated hydro code that lets her do some of the most really impressive high resolution simulations I've seen. All they're doing here is taking a gas disk and blowing up some supernovae in it. And you can see, naturally, the hydro is producing, well, the combination of hydro and cooling is producing a multi-phase outflow, which, again, violates this analytic intuition we have. What's going on here? Probably one of the big mechanisms is actually a kind of seeding mechanism that's very similar to how clouds are seeded. So if you take a bunch of small clouds embedded in a hot wind and then run that forward after a few, like 40 to 80 cloud crushing times, that analytic assumption says that there should be no clouds left in here. But you can see there are some clouds left. This is an idea that Mike McCourt came up with. The idea behind this is that these little cloudlets act like seeds in the cooling of this hot material. And more material from the hot wind ends up being accreted onto these seeds because of the mixing layer. So that Kelvin-Helmholtz instability that should be destroying all of these little rectangular clouds, these are one volume cell in these simulations, when you run this and turn on the refinement, the edges here mix with that hot material, puts them in an intermediate temperature. And does anyone here know for solar metallicity gas, around what temperature the cooling times are the shortest? Give you a hint. It doesn't actually really require metals. 10 to the 4, a little bit higher usually. But I guess I could also say, what is the most efficient mechanism for cooling? Recombination. Hydrogen recombination, exactly. So that happens a little bit higher than 10 to the 4 usually. But 10 to the 4 to 10 to the 5-ish. Basically, if you have gas but a little bit cooler than 1 million and a little bit hotter than 10 to the 4K, it's going to cool very efficiently. So if this wind is 10 million Kelvin and these clouds are 100 Kelvin, well, this mixing layer is going to have a lot of material in it that's around that recombination temperature. And that material is going to cool very quickly. And some of that mass is actually mass from the hot wind. So these individual little clouds that you might have started with that should be disrupted, well, it turns out that disruption process allows them to accrete material from the hot wind. This is a process that McCourt calls shattering, that a cloud will be broken into these little cloudlets, and those little cloudlets will start to accrete material from the hot wind, growing the overall mass of your cold component in the wind. This is wildly, wildly uncertain at this point, though. There is a ton of physics that we don't understand how it interacts with, thermal conduction, how magnetic fields interact. I mean, magnetic fields, but this is actually a place where that probably is pretty important. And it's a really active field of study. So we know that nature does produce multi-phase outflows. We don't quite understand exactly how she does it yet. So in terms of these outflows, which in my opinion are the most important thing in terms of reshaping the galaxy, ending the starburst period, for me, this is why I care about starbursting. This is what they do, is drive outflows. We see them in basically all starbursting galaxies. They drive winds faster and further if those same amount of stars are formed in a shorter period of time. Smaller clusters may not be important for driving outflows. And we think that they're ubiquitous up until about redshift 2. Basically every galaxy that is of any import is bursty until around redshift 2. The smaller ones stay bursty beyond that. And these bursts and outflows are typically multi-phase as well. So there's one last thing I want to talk about before we go to total discussion mode, which is, okay, starbursts happen, starbursts are common, and we maybe understand bits and pieces of how they drive outflows. But what do they do? Do they do anything beyond just shutting off themselves? So if you're a galaxy and you've entered a burst of star formation, what's going to happen to you? Are you just going to say, hey, I'm bursting for a while and then stop? Well, no, of course not. This would be, I wouldn't have this section if that was the answer. So I think that the big thing and the real reason I care about outflows and the connection that bursting starbursts have to outflows is this. This is a plot from Tumlinson, Peoples and Works annual review article on the CGM. And I think it's, for me, one of the most shocking plots that exists in galactic astronomy. Because if you look at this, the baryon fraction of observed galaxy populations, whether you're looking in the stars or the gas or the dust, is less than 30% of what it should be from the cosmic baryon fraction in basically every galaxy across the stellar mass range. Which, I mean, you can wave your hands about, like, all you have to do that is prevent baryons from falling in. If you heat your CGM up, accretion can stop before it hits the disk, easy to explain. But the missing metals problem is impossible to explain without winds. If you look at the metal fraction inside galaxies, they have less than 30% of the metals that their own stellar populations should have produced. A lot of those metals are in stars, some of them are in gas, some of them are in dust, but these are not metals that fell into the galaxy, these are metals that were made in the galaxy. So to get rid of them, there's only one way to get rid of them. Either to put them into black holes, which we don't think that that's actually a realistic scenario, where a significant fraction of the galaxy's baryonic mass is in black holes. We would have seen that. That's easy to detect. There's only one realistic scenario here, which is that you remove this material through outflows. So we think that it's really, really critical to be able to eject material from galaxies, both in order to get some of these scaling relations we see in galaxies correct. But for me, this is the one that's the most interesting because it's so easy to understand. If you make the metals in the galaxy and you can't find them, they had to have been removed. The other thing that outflows can remove, actually, is angular momentum. So in order to produce disky galaxies that don't have the majority of their material in their bulge, if you go back to early simulations, sort of the state of the art around 2000 or so, we were in a bit of a crisis. This is the angular momentum catastrophe that it was described at the time, which was it was impossible to make a disk-dominated galaxy. Now, part of that was the low resolution of the simulations at the time, but another part of it is that they were missing strong outflows. So here you can see in one of my simulations, the material that's being kicked out in outflows, the outflow rate, split into high angular momentum and low angular momentum material for two different models for feedback. And you can see that bursty star formation up to redshift 2 that drives a lot of strong outflows, almost all of the material that's removed there is at low angular momentum, material that would have circled into the center of the galaxy to form a bulge. So you need outflows to just, or not just to remove baryons, not just to remove metals, but also to preferentially remove those baryons that would otherwise fall into the center of your galaxy. Without this mechanism, every galaxy would be bulge dominated. And I think there's one final really, really interesting connection between bursty star formation and actually cosmology. So Lucio said at his talk that we're going to dip our toes into cosmology a little bit, and I want to dip our toes even deeper. So who here has heard of the cusp core problem? Okay, maybe a third to half. So the cusp core problem is this. If you run collisionless simulations of dark matter halo collapse, so some of the earliest simulations were exactly this to understand structure formation, you find this universal density profile, so the density of dark matter as a function of radius, for basically all galaxies. This is a classic paper, Navarro, Frank, and White, 1996. And it's a universal functional fit. Now, it is a functional fit, but it seems that this is the thing that galaxies do. And if you look at the inner regions of these NFW profiles, they have what's called a cusp. So the density continues to rise towards infinity as you get towards the center. However, if you observe real dwarf galaxies, there does not appear to be a cusp. There appears to be a core. The density, which you measure through the rotation curve, implies that there's a flattening out of the dark matter density profile in the center of dwarf galaxies. And this is really exciting because this means that we can use galaxy observations to constrain the cosmology of the universe. Because one of the ways that you can actually make one of these cores is by letting your dark matter not quite be cold. Either heat it up a little bit, so give it a little bit of a relic thermal energy, or by allowing it to interact. So either through self-interactions or slight interactions beyond just gravity with regular baryonic matter, which is, again, talking about we like black holes because they're cool. Wow, every dwarf simulator in the world in the early 2000s thought, hey, I can be a cosmologist now. I can prove or disprove lambda CDM just by measuring rotation curves. Well, there may be instead a baryonic solution, and I believe that the baryonic solution is the correct one here. Because remember, small galaxies are almost always in a bursty mode of star formation. They form stars not as one continuous smooth thing, but in these violent bursts. And those bursts eject effectively the entire ISM of the galaxy. And one of the things that about 10 years ago, a number of authors, probably the most cited one is this one by Ponson and Governado, realized was that what you're doing when you have bursty star formation that drives outflows from the centers of dwarfs is you pump energy just through gravity into your dark matter. You are adiabatically shocking your orbiting dark matter particles. They orbit on a short radius when there's a lot of material in the center. You kick that material out, and now there's no force pulling them towards the center in the same, well, there's less force pulling them towards the center. They migrate out onto a higher orbit, and when that material slowly accretes back in, they maintain some of that energy. So these periodic bursts, one after the other, each time injects a little bit of kinetic energy into your dark matter near the center of this galaxy. And because you're injecting kinetic energy, it moves on to higher orbits. You take that cusp and you turn it into a core. So go home thinking about the fact that understanding how bursty star formation works in galaxies isn't just important to understand star formation, galaxies, that kind of thing. It's actually important to understand cosmology as well. So when you actually simulate a galaxy with this bursty star formation, these dwarfs take their cusps and turn them into cores. So, takeaways for this. Outflows do a lot. They get rid of baryons, they get rid of metals, they get rid of angular momentum. The fact that we can see metals in the IGM and the CGM is really a smoking gun for this. We think that this angular momentum removal is important for building up disk-dominated galaxies. And in smaller galaxies, this bursty star formation may actually destroy those dark matter cusps, turning them into cores, and making hundreds of astronomers waste a decade trying to come up with new and exotic dark matter models. So, I want to leave us with some questions and some takeaways. So, don't think of starbursts as a separate kind of galaxy. Every galaxy has most likely had a period of bursty star formation in its past, and that period was most likely at high redshift. When you have mergers with gas content, wet mergers, you can trigger a starburst, but you don't need that to do a starburst. They drive outflows, which reshape the disk in many, many ways, including up to the dark matter profiles themselves. So I want to leave us with some open questions that we can think about and maybe add a few more things here. How much time do we have before? Am I... right now, we done? Yeah, I think we're done. Because I can't remember when I started. Yeah? Okay, well then let's leave this here. If you have one or two questions, maybe we can not go too over time. Cool. Yeah, hopefully some of you will answer these questions.
Maybe a couple of quick questions?
Hi, I have a very basic question.
Mm-hmm.
So in simulation, the limit for the star formation rate in this kind of systems, what is the number, more or less?
Oh, it depends on which simulation. So there is no single accepted set of parameters or algorithm for star formation, but generally they all try to produce stars in cold, dense gas. How cold and how dense, and whether there are other parameters as well that go into it, are going to vary. Every simulation, for the most part, has a different subgrid algorithm. So, for example, the ones I showed that I had done, those formed stars in gas that was denser than 10 atoms per cc, which is not very dense compared to a GMC, but that resolution limit is important. We can't get to 10 to the 4 atoms per cc in a cosmological simulation. At least we couldn't in 2015. But other simulations run at higher resolution might put that threshold much higher. Some also have requirements that gas be bound, that its virial parameter be small. Others include things like H2. So we don't actually have God's algorithm for forming stars yet. So it's really going to depend on which simulation you do. And that kind of, everything I said about simulations prove X. Simulations prove nothing. They suggest and predict, but they're all limited by the fact that a huge amount of the physics is subgrid.
Because I think I remember that at high resi from observation you can find 500 solar masses per year, maybe. And in simulation, at least TNG 300 is quite far away from the.
Oh,
from
well,
that.
don't get me started on TNG 300. We'll be here all day. But yeah, every simulation has its limits. TNG 300, the big limit is its resolution is very low.
All right, maybe one more quick question, if there's a quick question.
I think this question might be slightly deviate from what you focus on your lectures, but as a person studying the smaller scales, I'm just wondering like what happened the smaller scale if the burst galaxy, the starburst happened. I know the resolution is not that enough to reach the result of the GMC, but
No, that's a really good question. Like, I think it's a somewhat open question as to whether or not there is any difference in, say, a GMC at constant surface density in a starbursting system versus a non-starbursting system. One thing that it could just be is starbursting systems just have their star formation correlated in time, that all of the disk is forming stars vigorously rather than little individual patches. One of the things I'm most interested in the small scales is how do the outflows get out? So how do you get from inside a dense GMC to on your way out towards the virial radius? That's a huge can of worms.
Excellent. Let's thank Ben again.
Thank you. Do you want to use my clicker?
No, it's all right. I'll use the big pointy stick, I think.
Okay, big pointy stick it is. I just had it on here. You can use my power adapter if you want. Okay.
Hello, hello. Here you go. Thank you.
And next we have Johnny, who's going to talk to us about the galactic center of the Milky Way.
A bit higher. Okay. All right. I wanted to start with a bit of an apology, actually. I feel like I've let Steve Longmore down. And the reason for that is that at the conference dinner the other night, Steve would have ordinarily stood up and tried to embarrass our organizer and also say a big thank you, and I feel that wasn't said, so I would like to extend certainly my thank you. I'm not going to be here tomorrow, so I want to say a big thank you to Rainer for all of the effort he's put in organizing this. And the other reason for mentioning Rainer is exactly this. So the first time I actually met Rainer was 2 years ago at this StarFormation conference. We have a shared interest in the Galactic Center, and actually since that time, since meeting him, we've kind of planted the seed for a few projects which hopefully will start to bear fruit in a few years. Let's see what happens there. But this is just to say to the PhD students, you never know who you're going to meet at these meetings, and I think it's something that's very important. So, so my lecture is on the Galactic Center this afternoon. The outline, it's kind of in two parts. So I'm going to start with the what, and then I'll go on to the why. So I wanted to start with this statement. Before we get there, the Galactic Center is sort of by far and wide the most extreme star-forming environment in the galaxy, right? Roughly sort of 10% of all of the stars that have formed in the Milky Way over the last 100 million years or so have done so within just about 100 parsecs of the central supermassive black hole. That said, this statement, and this comes from a paper that was actually published by Steve Longmore about sort of 10 years ago or so, says that the present-day star formation rate at the center of the galaxy is about 10 to 100 times below what we might expect. And so, kind of, this was published about 10 years ago or so, and what's happened since that time is ALMA, essentially. So there's been a lot of work trying to explain why this might be the case. So for my introduction, I'm essentially going to step through this statement. I'm going to start by talking about this, so what I mean when I talk about the Galactic Center, because when I talk about the Galactic Center, it might be slightly different to kind of what Rainer might discuss. I'm going to talk about this, which is give you the actual star formation rate presently in the Galactic Center. And finally, the kind of the most important part of this statement, which is this. Right? So what do we actually mean by this? Expected by whom? Like, what is the expectation, and where does that actually come from? So starting here, Why are we interested in galactic nuclei? As Ben's just told us, black holes are cool, star formation is cool, right? So massive galaxies have supermassive black holes at their centers, but also galactic nuclei can account for up to 80% of a galaxy's star formation rate in certain cases. And as we've just heard, thanks to that lecture from Ben, the activity that goes on at the center of the galaxies, whether that's via nuclear starburst activity or potentially the activity due to the central supermassive black hole itself, are kind of key components in what ends up driving galaxy evolution. More specific to star formation is going to be demonstrated here. So this is a plot that's taken from a review, which should appear soon. This is by Ava Schinner and Adam Leroy looking at nearby galaxies. This is actually work from Jai Sun from the FANGS collaboration. This is plotting the mass per unit area, so the surface density, versus the velocity dispersion here on the y-axis. Each data point here is referring to a region in a galaxy. This is not identifying individual clouds. This is not cloud finding. This is basically hexagonal regions within a sample of galaxies and just looking at the properties within those galaxies. So it's kind of closer to that pixel statistics methodology that I was talking about on Monday. So this is over a sample of about 100 galaxies, and we can look at the properties. And what you can do here is you can segment your galaxy into different regions. So we have galaxy disks, and then you can segment that a little bit further, and you can say, okay, this is where the spiral arms would lie, and then this is kind of interarm regions. The point is that, you know, in the galactic disk, you're kind of occupying this lower part of the plot here, so, you know, sort of fairly average surface densities, fairly low velocity dispersions. Galactic centers occupy this part of the plane. Right? So incredibly high surface density, incredibly high velocity dispersion, a lot of kinetic energy in the gas. In the context of our own Milky Way, the galactic center is really important because I think it's fair to say that the vast majority of our detailed understanding of star formation comes from a handful of molecular clouds that are located within just a few hundred parsecs of the sun. What I mean by that is where we can actually go and we can directly observe, you know, the different phases of the star formation process, where we have models to describe what we see, et cetera, et cetera. But the physical conditions there, as we've just seen, are relatively benign in comparison to what's going on in the galactic center. So what the galactic center offers is a region of parameter space whereby we can really test our understanding and our models of the star formation process that's going on there. I think it was Ben that mentioned over dinner the other night that one of his favorite things to do is to break models, right? If you want to test a model, your model for star formation, go and test it in the galactic center, right? From the extragalactic perspective, it's kind of a Rosetta Stone, right? The galactic center is, you know, imperfect in some ways, right? The star formation rate is currently low. There's no exciting AGN, right, currently, etc. But it's the one that we've got, right? And it remains the only galactic center where we're actually able to resolve the physics of star formation from 100 parsec scales down to the scales of individually forming protostars, and it will remain that way for some time. So understanding star formation in this location is a really important data point, effectively, for understanding how stars form at the centers of other galaxies, but also how stars may form in more extreme corners of the universe, essentially. All right, so part of the reason why studying the galactic center is difficult is captured here. This plot, which blows my mind every time I see it. Nuria showed this the other day. I find it astonishing that this is star counts, right? This is basically a histogram. This is Gaia's view of the sky, right, in the optical. But what you can see here, or perhaps what you can't see, and this is the point, is that our galactic center is completely obscured in the optical, right? So if you want to learn about the galactic center, we have to go to longer wavelengths. So this is Spitzer's view of the galactic center. So this is in the mid-infrared. Each of these panels is going to tell you what the different colors mean up here somewhere. Just to highlight a couple of interesting features here that you might see already with your eye. So galactic center is here. What you're actually looking at, this bright spot here, is the nuclear star cluster, the most dense star cluster in the galaxy. We also have other star clusters. These were mentioned today. So we've got the Arches cluster here and the quintuplet cluster. These were mentioned in Ignacio's talk today. So these are examples of young massive clusters, 10 to the 4 solar masses of material, radii of about a parsec, and ages of, you know, a few million years, maybe 4 million years or so. And then the other thing that you might see here that might draw your eye are these dark patches. Right? These are the dense, very cold molecular clouds in the galactic center that are obscuring all of that background starlight in the mid-infrared. So what we can do, if we want to go from extinction to emission, we can begin to fold in longer wavelengths, and this is now folding in Herschel observations. What you begin to see is this dust in emission rather than extinction, right? So all of a sudden you see these molecular clouds begin to pop. You also see all of this additional material out here. This diffuse should really have kind of quotations on there. This is diffusing galactic center kind of context. This is not diffuse gas at all. But then you also see other regions of interest. So for example, where the embedded star formation is beginning to heat its local environment. So for example, here at Sagittarius B2, you can see this start to shine brightly as well. We can go to even longer wavelengths. We can now fold in the radio. So this is now folding in observations from Meerkat. And here we begin to see the impact of feedback, which has been prominent throughout this conference as well. So here we see the impact of H2 regions surrounding high-mass stars. We also begin to see evidence of supernova remnants, which become really prominent here as well. So this is what I mean when I talk about the galactic center. I'm talking about everything that's within a galactocentric radius of about 150 parsecs, give or take. And in that region, we have the whole range of phases of star formation activity. I don't have anything else to say here. This is just because this is a really nice figure. So this is the Meerkat image of the galactic center. All right, moving on. So how do we measure this? What is the present day star formation rate in the center of the galaxy? So this is just to give you the number. The present day star formation rate at the center of the galaxy is about 0.1 solar masses per year, give or take. And we can, because the galactic center is at a distance of only about 8 kiloparsecs, we can actually measure this in different ways. And Mark gave some insight into how we actually measure star formation rates from our observations in his talk, I think on Monday. So we can do this in different ways, and Mark mentioned both of these. So the first way that we can do this is, because it's only 8 kiloparsecs away, we can actually go and we can just count sources, right? And the sources might be different. We might be looking at young stellar objects. We might do this with H2 regions. We might do this with supernova remnants, etc. But if you know the IMF, and from stellar evolution, you kind of know the timescale that's associated with that emission, you can derive a star formation rate from in this way. The other way that we can do this is
I'm just curious about what the spread in star formation rate from different ways of doing this tells you about the method. Like, it says anything about the methods, right? Like, you go from 0.01 to 0.15.
Yeah, okay. So be careful reading this sort of the absolute variation in these numbers. There's a lot of uncertainties. I'll come back to this, but the key point here is it's not 1 solar mass per year, and it's this one in particular is definitely underestimated. It comes down to how you attribute those sources and kind of what you do in your analysis. So just be careful there. But it's of the order of about 0.1 solar masses per year. But there's obviously absolute uncertainties in each of these measurements that will contribute to those differences in some ways. The other way that we could do this is more similar to what you do in extragalactic observations. So we can actually take integrated light measurements. So we actually measure the emission over a given region in a particular frequency, a particular wavelength. So there's 3 different, I forget individually which each of those are, but they're basically at Spitzer and Herschel wavelengths. And if you cast your minds back to Mark's talk, the important thing here, so you have to have an associated timescale with that emission. We give a range here in this table. This is overestimated, but because of the emission that we're actually looking at here, what we can't do is rule out interlopers, essentially, in producing that emission that isn't necessarily related to star formation activity. And so the average timescale associated with these emission sources is much closer to the 5 than it is to the 100. But that just kind of encapsulates the fact that we might have kind of contributions from other things that we're not super interested in this context. The key point here is that the different methods tend to agree. right? Integrated light, we have many different independent measurements here looking at different types of sources, you know, source counting, integrated light measurements, the different measurements, you know, agree. It's not a solar mass per year, and it's not really sort of 0.01 solar mass per year. The second takeaway is the fact that these different methodologies are sensitive to different timescales. So what we can say because of that is that the star formation rate has been, at least on average, close to this 0.1 solar mass per year value over the past sort of 5 million years or so. What we can't rule out is kind of delta bursts, right? So where you might have a sudden increase in the star formation rate that kind of gets washed out over those 5 million years or so. But, you know, on average, this seems to be what the star formation rate is presently. So this is kind of just delving into that kind of burst idea. What we do know is, for example, we have the arches, we have the quintuplet cluster. These have ages of the order of a few million years or so. At the very center of the galaxy as well, there's also a population of young, massive stars at the order of about 5 million years or so as well. So this is what I mean, where we might have kind of short fluctuations in star formation rate within that kind of 5 million year window or so. The other thing here is if you average over longer timescales, so this is work of Paco, but also Reiner was heavily involved in this work. Here they're looking at stellar populations in the nuclear stellar disk, and I'll come on to what that is in just a second. But if you look at those stellar populations and derive star formation rate from there, you see that it might be actually a little bit higher in the past, factors of several higher in the past, depending on how you do this. So what this is telling us is that the star formation rate at the center of the galaxy is of the order of about 0.1 solar masses per year, but that isn't to say that it wasn't higher than that in the past, right? There might be some time variability associated with it. All right, expectation. Where does this come from? So the expectation comes from empirical star formation relations, and Mark has introduced us to many of these over the past few days. So, you know, there's different flavors of this, but philosophically, they're all kind of the same. What you want to do is you want to compare or relate the rate at which you're forming stars in a particular environment or in an entire galaxy to some property of the interstellar medium that you deem to be important for star formation, right? That might be the total amount of gas, it might be the molecular gas, in this case, the amount of dense gas. Okay, so this is sometimes referred to as the dense gas star formation relation, sometimes the Gauss-Solomon relation, the Larder relation, there's different flavors. And actually, I'm combining different relations here. What the x-axis is a mass of dense gas that's measured above some threshold in either density or surface density. And you have the star formation rate on the y-axis. I'm going to come back to that in just a second. But in principle, what you see is a very tight, there is some scatter, but a tight linear correlation in these two variables over many, many orders of magnitude, both in mass and in the star formation rate. Right, what I mentioned there was I'm actually combining two different plots here. So the original kind of paper on this looked at extragalactic observations. It was the Gauss-Solomon relation, right? And what they were actually measuring was the intensity of HCN, right, a dense gas tracer. From Mark's lecture, he told us that the critical density of HCN is about 10 to the 4 particles per cc. Charlie Larder and his collaborators then looked at this kind of relation, but in nearby molecular clouds. They were looking at dust extinction, measuring column densities of the dust. What they noticed is that there was a strong correlation in the locations of where you have stars in regions of dust column density above about 120 solar masses per parsec squared. Okay? If you assume that those stars are forming in cores, which are quasi-spherical with radii of the order of about 0.1 parsec, and you just assume a sphere, you convert that surface density into an actual density, you arrive at this 10 to the 4 particles per cc, right? And that then immediately allows you to make the connection between nearby clouds and extragalactic sources. Okay? Is that clear? So it's kind of the combination of the two. So if you take this relation at face value and you say, okay, so there's a correlation between the mass of dense gas above about 10 to the 4 particles per cc and the star formation rate, we know that the mass of the galactic center of the central molecular zone is about 10 to the 7. You would say that you would expect to have a star formation rate of about a solar mass per year. Right? And we don't see that. So the CMZ sits here. The insert image here is just kind of normalizing that. So we're just actually removing this relationship and we're just plotting this. So you kind of emphasize the scatter. So there is definitely scatter in this. But you see here that the galactic center sits, at least an order of magnitude, even more when you take into account the uncertainties, depending on how you measure the star formation rate, etc. So that is where ultimately the kind of this expectation comes from. So it's the assumption that if star formation is behaving as it does, say, for example, in local molecular clouds, then you would expect to find this star formation rate of about a solar mass per year, and we don't see it. All right? So that's where, in that initial paper from 2013, the expectation comes from. The other thing here is about the time variability. So what you can do is you can look at, for example, the Milky Way central molecular zone, and you can compare it to the centers of other galaxies. So this is just, this is an example M83 here. So in many of its physical properties, so in terms of the gas mass, the stellar mass, surface densities, line widths, etc., very, very similar to the there are differences, but very, very similar to our own Milky Way central molecular zone. But the star formation rate is an order of magnitude above. Okay? So there seems to be some allowance for variability in this, which is then, so what's actually going on with our own galactic center? Do we just happen to be observing our galaxy center at a time in its history, right, bearing in mind that the star formation rate has been higher in the past? Are we just observing it at a time where the star formation rate happens to be low now? It's just an auspicious time. And or, because these two things aren't necessarily mutually exclusive, is something actively inhibiting the star formation process at the center of the galaxy presently? So that is the kind of the situation in 2013, right? This paper came out and that kind of reinvigorated a lot of interest in galactic center science over the decade that followed, and the kind of the big driver behind that was ALMA, essentially. So this then brings us on to the why. So people then spent the past decade trying to understand why this might be the case. And if I was to kind of bundle that 10 years of research and do it total disservice and try to put it into a single statement, this is kind of what you would find. So the kind of the point here is, well, there's several, but the central molecular zone is not an isolated system, first and foremost. And that the star formation here is regulated by both large-scale dynamical processes and the extreme local physical conditions in the interstellar medium. Right, so just like in the first part of the talk, I'm going to walk you through this statement and explain what's going on here. So the galactic center is not an isolated system. You have to think about it more like an ecosystem, which is depending on the gas coming in, what's going on, the star formation, gas flowing out. So okay, you have to kind of consider all these things together. We have all these different phases of the star formation process there. I'll talk a bit about how large-scale processes help to drive both temporal and spatial differences in star formation in the center of the galaxy. And then finally get on to discuss how the physical conditions in the ISM there might actually impact the star formation process. All right, so let's start here. So let's take a step back. Why do we have a central molecular zone in the first place? So does anyone know what is perhaps the single and most important feature that can be seen in this plot? This is a sort of top-down schematic of the Milky Way that tells us why we might have a ring of molecular gas at the center of the galaxy. Can anyone have a guess to what feature it is?
Those two incoming streams.
They're important, yeah. They're part of the one I'm talking about, yeah.
The galaxy's bar.
It's the bar, yeah. So as with two-thirds of galaxies, the Milky Way hosts a stellar bar. This plot is showing you how the bar actually impacts the potential, or what components in terms of the stellar components are dominating the gravitational potential of the galaxy as a function of radius. So the x-axis here is galactocentric radius, location of Sagittarius star at 0, and this is the enclosed mass, okay? So what this is showing you is out to about sort of, a couple of parsecs. This is the line that's for Sagittarius star. Sagittarius star is dominating this is Sagittarius star, so Sagittarius star dominates the potential out to here. Once you get to here, the nuclear star cluster begins to actually dominate the potential. Here you have the nuclear stellar disk, which roughly is similar, much more massive than the gas mass in the central molecular zone, but roughly covers a similar kind of area. And then beyond that, up here, the galactic bar dominates. And the reason that's important is because beyond just a few hundred parsecs, the central molecular zone is here, the potential is highly non-axisymmetric, right? So the first step to understanding how gas moves in a non-axisymmetric potential is to consider the orbital structure. So in a non-axisymmetric or barred potential, there's kind of two important families of orbit. So in the yellow here we have X1 orbits. These are elongated elliptical orbits which are parallel to the bar, so in this direction. And then inside those we have so-called X2 orbits, which again, elliptical, getting more circular as you get to the center, and these run perpendicular to the bar. These are sometimes called ballistic or stellar orbits, right? This is how, if you were to look at a numerical simulation of an isolated Milky Way type galaxies, this is what the stars would be following. The gas is slightly different, right? Gas is only happy to follow these orbits where the streamlines don't cross, right? So gas will self-intersect, it will interact. When it does that, the gas is able to lose angular momentum and it traverses inwards along to sort of smaller and smaller orbits and move inwards. So the mass moves inwards, angular momentum moves outwards. Similar to what Patrick was discussing in his lecture, a different orbital configuration, but basically the same principle. What you see when you move to smaller and smaller radii is that the X1 orbits become more and more elongated to the point where they actually become self-intersecting. Okay? The gas does not like this. The streamlines cross. Right, this is my pop culture reference that shows my age. Despite my, some of my scientific opinions, Ghostbusters being the best film of its generation is absolutely a hill that I'm willing to die on. So,
Did you see it in the field?
Huh?
But did you see it in the field?
I'm not that old.
Oh, you played yourself.
But it is my favorite movie of all time. All right, this is showing this in action, essentially. Okay, so this is a numerical simulation looking at different components of the interstellar medium. We've got the total gas here. So this is an isolated Milky Way-like galaxy taking an observationally motivated Milky Way potential. H1 gas, H2, this is actually the star formation rate, and then the CO. Right, and what you see here is out here, you see these kind of X1 orbits, it's kind of rotating around like this. But something important happens here, right, where these orbits become cusped. Here, the gas interacts, collides, it shocks, and then it moves inwards along what we call these dust lanes, right? Dust lanes is a historical term. Sometimes we're sort of getting more to the point of calling them bar lanes. They're effectively showing you the shocks that actually mediate the transition between X1 and X2 orbits closer in towards the center of the galaxy. What you see then is that this then settles. Maybe I can show this again. It settles into a ring here, which approximately following those X2 orbits and perpendicular to the bar. Yeah?
So the X2 orbits.
So the X2 orbits live at a lower angular momentum than the X1 orbits. Is that kind of a true statement?
Well, essentially, it's just the angular momentum just governing the mass transport inwards, right? Yeah. So the dust lanes, we see these in external galaxies, right? So this is what you see if you could look at kind of at the Milky Way and from the top down. This is a beautiful image from the FANGS collaboration. This is some combination of sort of Hubble data, and you see here these dust lanes, which are this transition from X1 to X2, moving towards the center. This is just to kind of hammer the point home that bars are important. So this is actually some work from Sophia Stuber, who's a PhD student of Eva Schinnerer at the MPIA. As part of the FANGS collaboration. She took the FANGS sample of galaxies and then looked to see which of those actually have central rings. And it turns out that if you look at the barred spirals, about 60% of those have central molecular zones that, qualitatively, in the sense of, looking like central rings, look very similar to our own central molecular zone. Yes, Rainer.
Not a fully related question, but some I always want to ask. It just pops into my mind. Is the fact that we see rings here related to stellar density or stellar population? Because I mean, there's always this
yeah.
nuclear disk ring kind of thing.
So you mean once
but
the
could there
stars
be a
form,
nuclear
you're getting
stellar disk,
spread out?
and
Yeah.
the ring is just marked because it's just now actively forming star? It may be moving out or in.
Yeah,
or
I
whatever.
understand. That's not really a question that I can answer. I don't know the answer to that question. It's a good one, though. Yeah. She's been, so Sophia, she sent me this figure. She's largely been working on actually characterizing the morphology in the molecular gas. But this was just a prettier picture. But it's a great question. Yeah.
I was just curious, are these all on the order of 100 parsec scale?
No, they're not. No, because it depends on the bar. Depends on the size of the bar. So you can have, for example, central rings which are, or you can have, so you know, so configuration, we have the central molecular zone, and then we have the kind of the central circumnuclear disk or ring at the center of the galaxy. Some circumnuclear disks can be the size of our central molecular zone. What actually sets the size of central molecular zones in galaxies, actually this is an important conversation for the conversation we were having the other day, it depends on the galactic bar, but we don't know precisely what sets the size of the central molecular zones. To some extent, the way you can think about it is, to some extent, you know, the central molecular zone is approximately following an X2 orbit, but there's many X2 orbits, and there's nothing to really say currently what actually is, which ones of those are populated and which ones are not. Yeah. Yeah. All right. Okay, I'm going to really struggle for time. Okay, so the central molecular zone is not isolated. And is fed by the gas that's actually transported to the bar to the center of the galaxy. Okay, so how does that affect star formation? One way to think about this is to ask what happens once the gas enters the central molecular zone. This is really similar to what Ben was just showing us earlier. It's basically this idea of a bathtub model. Okay, so on the left-hand side, it's just set up in a slightly different way to what Ben showed. On the left-hand side, we have m dot in. This is the rate at which you're actually transporting material to the center of the galaxy. On the right-hand side of this equation, you can think about this as the kind of consequences of what's actually happening to that gas. Okay, so it's either going to form stars, it's going to be expelled from the center of the galaxy, or the actual mass in the central molecular zone itself, so the ring of gas that's orbiting the center of the galaxy is going to grow, or it's going to change. Okay, so that's the rate of change of that. So I've told you this, right? We can look at this in the context of measured quantities. You know that this is about 1/10 of a solar mass per year. All of these are measured in solar masses per year. We can have a go at measuring this. So this is some work of Matthias Omani and Ashley Barnes. The challenge here is, unlike obviously looking at nice face-on external galaxies, we have to use other techniques because we're looking through the plane of the galaxy to actually determine where those dust lanes are and how to attribute mass to them. And the way that we actually do this is by looking at diagrams like this. So this is a longitude velocity diagram, and you see these kind of high velocity streams here, which is what Mattia and Ash attribute to being the equivalent of the dust lanes or the bar lanes in our own galaxy. And then you see them projected on where they are on the plane of the sky in this image here. So they take the emissivity of CO, right? They convert that into a column density of CO. They then convert that using some assumptions into the column density of H2. They then derive a mass of that H2, and then they basically make a little toy model of how gas they think is actually flowing into the center, and from that they derive a accretion rate into the central molecular zone. Okay, so many assumptions. There's a big twiddle in front of all of these numbers. This is arguably even harder to measure for precisely the reasons that Ben was talking about earlier. We have a kind of a multi-phase outflow. We know that gas is outflowing from close to the center of the galaxy, right? This is the famous Fermi bubbles in red. And then you have the X-ray emission here. This is seen by E Rosita. This is 14 kiloparsecs above and below the plane, right? So we know that there's an outflow or relic outflow from close to the center of the galaxy. If you actually look at the meerkat images, we also see a much smaller outflow, as in physically on the plane of the sky, outflow in the radio as well, which is thought to be kind of a chimney, which may actually be feeding the kind of the Fermi bubbles. But because it's a multi-phase medium, you can make some attempts to actually calculate the amount of mass in each of those phases, and then assuming in a kind of an expansion rate, you can then derive an outflow rate, an expansion velocity, sorry. You could derive an outflow rate for the outflow. Right, big twiddles in front of all these numbers, big tildes. If you just take these numbers at face value, right, you can say, okay, well, does this mean that actually the central molecular zone is growing in mass, potentially? Or perhaps, you know, we're roughly in about balance, okay? So what does this mean for the temporal evolution of star formation? So two different simulations here. Simulations largely return slightly contrasting results on this, which might be due to the simulations themselves. But two different numerical simulations here of Milky Way type galaxies, isolated Milky Way type galaxies. They use very similar, Mark, I'm looking at you, or perhaps even the same potential here. So Armilotta and Matthias Omani. It's very similar, right, in terms of the potential, the setup of the simulation.
I know. Matthias changes over time.
Yes.
So I don't know which this was done.
Okay. I think they're basically pretty similar setup, but perhaps differences in things like the feedback prescriptions, etc. Key differences here, what you're looking at is how the star formation rate changes as a function of time. So in this simulation on the left-hand side, what you see are these little bumps, right, in star formation activity. This is just a power spectrum of that, where you see this sort of peak at around 50 million year timescales. The interpretation, roughly, at least in a qualitative sense of this, is that the mass builds up in your central molecular zone, becomes highly gravitationally unstable, you collapse and form lots of stars that generate lots of feedback. And then what happens is the first supernovae go off, and that injects a hell of a lot of energy into the interstellar medium, right? And then you have to wait for that energy to actually be dissipated before the process can actually start again. So you need to get rid of that energy before you're going to collapse again. So you have this kind of quasi-periodic but bursty changes in star formation activity. On the right-hand side, the picture is slightly different. Right, so the mass in the CMZ is slowly growing over time, and the star formation rate kind of follows that increase in star formation activity. But the point here is that the actual star formation activity at the center of a galaxy is somewhat related to these large-scale physical processes. There are other simulations that, for example, use a time variable inflow rate, but controlled rather than looking at a simulation of an entire galaxy, and how that leads to bursts in star formation activity. Right, so the combination of how much gas is inflowing and then the impact of feedback and how that actually affects things as well may contribute to this time variability in the star formation rate in the galactic center. Okay, in terms of the spatial variation, I'm going to go through this really quickly. I might skip some stuff here, but spatial variation in star formation is also important here. There's an argument to say that star formation may actually happen at a preferred location in nuclear rings. So one idea which is expressed here on the left-hand side is that just that it's random, right? We call this the kind of the popcorn picture, right? So the ring itself becomes gravitationally unstable, but there's no kind of favorable configuration to where actually you're forming stars. On the right-hand side, this kind of pearls on a string model is where you actually have a specific location where star formation may be actually triggered, okay? And so this has been supported by some observations of nearby galaxies in which what you find is you have an age gradient in clusters along the central ring. Okay, so you actually have a preferred location where star formation gets kicked in, and then you have this kind of sequential star formation sequence in your nuclear rings. And this is important, I think, in the context of what Ben was saying, right? If you want to drive nuclear starburst activity and think about how that potentially might affect how your galaxy evolves over cosmic time, you need to coordinate that star formation activity in space and in time, right? Getting those two things together is super important. This is just illustrating that. Okay, there's two different ideas here. So the trigger point for this is potentially where actually that gas is crashing into the central molecular zone. It's coming along the bar, enters the central molecular zone, and it interacts with gas that's already orbiting on those X2 orbits. That drives the density up. That's your trigger point, okay? This is then demonstrating that particular idea. This is a numerical simulation. It's just to highlight to you where the gas is actually inflowing in this simulation. You've got the central ring here, and then at apocenter in this picture, you actually have where you get these high densities and where you get the star formation triggering. Here, as we move to the center, this is now the surface density of young stars in the ring, right, which you see shows a slight enhancement once you are down center from apocenter. And then here is just kind of looking at the azimuthal average, right? So looking at this around the ring. And then this is again the surface density of young stars. So you see there's kind of, once you just past apocenter, easier to see here, you then get this kind of ramp up in the surface density of young stars past the trigger point, okay? So the trigger point is here, takes time, and as you rotate, that's where you get the increase in the surface density of the young stars. There's some observational evidence for an alternative picture in our,
Yeah, sorry, this might be a bit of self-promo, but if you go one slide back, we have been able to do this in a cosmological zoom-in simulation until redshift 4, I have to say. So we're not going to redshift 0, and basically we find more like the cluster, like group popcorn kind of situation forming there, and also with the star formation, we find actually also a very bursty one. What I found very interesting, but we didn't go in further, is actually it anti-correlates with the star formation rate in the center of the nuclear star cluster. Why? No clue.
Okay.
But that's, I just wanted to have said that we slowly are trying to do this also more in cosmological zoom-in simulations.
Awesome. Yeah, that's really cool. Just to kind of comment on the first part, in general, like if you take individual, so this simulation, if you take individual time steps, you know, any moment, any sort of snapshot in time, you know, the chances are is the popcorn kind of dominates. It's only when you can time average, right, in the simulation where you actually, these trends actually begin to pop out, where you might actually see, so it's very tentative, and popcorn and or this idea is kind of preferred to the other one, which I'm about to talk about. But yes, certainly tentative, but any individual time, of course, we don't have the beauty of having access to time in our observations. But yeah, that's the kind of the general idea. What we do have is potential evidence for a sequence of star formation, but not at apocenter, but actually at pericenter. So again, this was an idea by Steve Longmore, where as you make your closest approach to the bottom of the galactic gravitational potential well, if you have a cloud which is approximately virialized, as you get closer, you're going to feel the variable impact of the potential as you circle the ring. So it's going to be stronger at pericenter and less strong at apocenter, where you're further away from the center of the galaxy. And that might just give a kind of push to those molecular clouds, right? Just might tip them over the edge and towards collapse. And this comes from this part. So this is the pericenter passage model or idea. It's not really a model, but so what we're looking at here, this is a top-down view of this picture. This is corresponding to this. Of course, we're looking through the plane, right? So everything in here is captured in this image. So both front and back side, right? Which is why it makes this difficult. Very quickly, we have a cloud like the brick, and I'm going to come back to this, has very little signatures of active star formation. We move along the ring, get to Sag B2, lots of star formation. I'm going to come back to both those clouds. And then assuming some sort of geometry for the 3D structure of the ring, which you see here now in the hot gas tracing H2 regions, is larger and larger H2 regions kind of following this idea of the model. So potentially this idea of some progression in the star formation activity. All right, initial conditions, or physical conditions in the ISM. What do I mean when I say extreme? Okay. The central molecular zone with a galactocentric radius of about 150 parsecs covers, you know, 0.1% of the surface area of the galaxy. But it actually contains about 3 to 10% of the molecular gas mass, right? The gas here is dense. You can see it here. This is another dense gas tracer. Again, in terms of thinking back to Mark's lecture, this has a critical density of 10 to the 4, 10 to the 5 particles per cc. This is the central molecular zone absolutely booming over the entirety of it, right? This is just another example. This is the line width size relationship, which has come up a couple of times throughout the school. So it's showing you the size of clouds here versus the line width. This is galactic disk clouds, kind of classic Larson relation here with some scaling. These are the galactic center clouds, right? There's been some argument about the slope and what the actual slope is in the galactic center. You don't really need to care about for the purpose of this lecture. The point is the vertical offset, right? So for a fixed cloud size, line widths are much broader. There's much more energy in the gas, right? Much more dynamic. And this translates into many of the physical conditions that we find at the galactic center. So turbulent motions, magnetic field strengths, gas temperatures, densities, pressures, cosmic ray ionization rates. You know, these things can all be orders of magnitude greater than what we actually observe in nearby molecular clouds. And that has an impact on many different things that are related to the star formation process. Here we're looking at the same group of clouds that are highlighted where we had that sequence. So I highlighted the brick, which is this molecular cloud, and SAGB2. So just a kind of closer look at those. So this is the brick. It is one of the most massive and dense molecular clouds in the entire galaxy to not exhibit signatures of widespread high mass star formation. Okay, it is forming stars, but very few stars, and they're typically low mass. Right? To put the brick into context, we've heard a lot about Orion. This is the Orion A and B molecular clouds, right? This has the same mass as this, right? So somehow the universe has figured out a way to put all of that mass into a cloud of that size and to stop it from forming stars, right? This is the equivalent of a duck-billed, venomous, egg-laying mammal in terms of molecular clouds, right? Then you have Sagittarius B2. This poops cubes. No, I'm joking. I've realized that's going to be really confusing on the recording if no one's... yeah. All right, SAGB2 is one of the most massive molecular clouds in the galaxy, 10 to the 6 solar masses of material. It accounts for half of all of the present-day star formation in the galactic center. Right, so coming back to this plot here, this idea of a kind of universal density threshold for star formation, which is how this was put forward. This is where the expectation comes from, and the galactic center doesn't fit in with that picture. Let's look at that in a bit closer detail. So how might these physical conditions actually impact what's going on? I've tried to make this plot is extremely information dense, so I've grayscaled it to start off with, right? Just ignore it's just a stacked bar graph, just ignore the actual individual parts of the bar graph to start off with. What it's showing you are different clouds, different regions of the galactic center, okay? The y-axis is kind of a poor man's approximation for dense gas fraction in these clouds. What we're actually doing is we're looking with an interferometer, which is the SMA. We see the contours, significant contours of emission in the dust continuum. We measure the mass within those compact structures looked at with the interferometer, all right? We're then dividing that by the total cloud mass, which we're deriving from Herschel observations. So it's kind of like how much mass is in compact substructures versus the entire cloud, the parent cloud itself, okay? What you see here, this is sort of 10%, so less than 10% of the mass of these clouds is actually contained in compact substructures. Actually, on average, it's much smaller than that, right? So you don't have much of, even though the gas is all high density, there isn't much of it that's actually contained in overdense regions. Right? And that's what you see in here. So bringing in the color scale now, and I'm just going to focus on the brick and Sagittarius B2. What you see here is in the brick, so this is telling you the fraction of gas that's actually in column density bins, okay? So the difference between Sagittarius B2 and the brick is, you know, okay, maybe some factor of 2 in terms of the amount of mass that's in compact structure. But the compact structures that we do see, the ones where we see in a very high star-forming cloud, are at much higher column densities. This is column densities above 10 to the 24 particles per square centimeter, whereas that's not the case in the brick. Showing this another way, going back to that pixel statistics that I showed you in my lecture on Monday, right? This is Sagittarius B2. This is work of Adam Ginsberg. The black histogram here is a column density PDF taken over the field of view of Sagittarius B2. Red is the column density PDF of pixels that are associated with protostars or very close to protostars within one beam. Blue is the rest of it that's not near a protostar. The black line is the ratio between the red and the black curve. So what you see here is once you get to, so the mean density is of the order of a few 10 to the 23, right? Once you get to 10 to the 24, right? You're quickly finding that all of the gas is associated with protostellar sources. The point here is it's not the density. All of the density is super high in comparison to nearby molecular clouds, right? Orion's down here somewhere on this plot, right? It's the overdensity, right? You need to push the substructure in the cloud to higher overdensities. This is showing that in the brick, exactly the same point I made. This is the mean density and the column density in the cloud. Right? This is a factor of 10 higher than that. This is the only known location of star formation in the brick. right? We see this here. This is work of Dan Walker. These are actual outflows detected in SIO. So these are where the stars are forming in the brick. They're all low mass, the piddly little things. No high mass star formation, but this point remains. The key point here is that this idea of a universal density threshold at 10 to the 4 particles per cc doesn't work in the galactic center, okay? What you need to do is actually consider the other physical conditions that are important for star formation, the fact that the gas is incredibly turbulent and there's other stuff going on. So this is the idea of this critical overdensity. This is kind of from some of the models in Patrick's talk yesterday, day before, right? So this is that the critical overdensity required for star formation is proportional to the virial parameter multiplied by the Mach number squared. Okay, the exact detail, this is just an illustration, but the exact details don't matter so much. Right, if you actually put some numbers in for solar neighborhood clouds and galactic center clouds, right, so typical Mach numbers, for example, typical like mean densities we're actually observing, right? The mean density is already kind of a 10 to the 4 particles per cc in the galactic center. What you derive here is that the critical density required for star formation is not 10 to the 4 particles per cc in the galactic center. It's more like 10 to the 7. Right? You need to push the gas higher to higher densities. All of the gas is at higher density. So the kind of message here is that there's nothing wrong with this. The problem's with the expectation. Right? If this was actually accounting for gas above the local critical density for star formation that depends on the local environmental conditions, what's going to happen is you're going to have less mass at that density. The brick is, the galactic center is going to move leftwards on this plot. Right? The other way to think about this is that this is not a static point in this plot. The galactic center is going to move around in this. Sometimes it's going to be above the diagrams, the relationship. Sometimes it's going to be below the relationship. We know that because of past star formation activity where the star formation rates were higher. On average, maybe it agrees. We don't know. All right, so coming back here, are we presently observing the galactic center at a low point in its star formation history? I think so, just purely from the evidence that we know that the star formation rate has been higher in the past. Is something actively inhibiting star formation rate at the center of the galaxy? I think it's just a natural consequence of the fact that the physical conditions are extreme, right? And so then we therefore have to think about how we actually interpret plots like that, dense gas star formation relation. Whew, okay. Made it. All right, I'm actually not going to go through the conclusions. If you are interested in this, we wrote it all down for you, right? So all the details are actually in here. Of course, you can ask me any questions that you might be interested in, but we wrote a review for Protostars and Planet 7. All the information is in there. What I do want to highlight actually is this, right? So this kind of brings us up into, the present, let's say. What happened after that result in 2013 and the onset of ALMA was we all went with ALMA and we observed individual molecular clouds, and we did so at heterogeneous resolutions, sensitivity, spectral setup of like individual molecular clouds. And because everything was kind of different, it made it very difficult to compare results between different molecular clouds in the galactic center. So a few years ago, we went away and we applied for we were successful in obtaining an ALMA large program to observe the entire region that I've just been talking about at 0.1 parsec resolution. Okay, so a uniform, contiguous survey of the entire galactic center. This is one of the molecules in our spectral setup, observed at the physically relevant scales for star formation, getting down to about 0.1 parsec scales. So this is the kind of the result of that. This is what we're working on now. The data is getting to a point where it's almost science ready. It's going to be the largest mosaic ever created by ALMA. There's something like 5,000 pointings that are required to actually cover the region. And the data are beautiful. The other thing, and this brings me back to Rainer, full circle, is something else that we're really interested in. We recently, as a result of many of the conversations that I think started at the Star Formation School and at Galactic Center conferences over the past couple of years, we tried to mobilize the community in the context of JWST and kind of come up with what are a list of questions that JWST is going to be really instrumental in answering over the next few years. The output of that was a white paper, community survey of what we would like JWST, what questions we would like that to answer, that kind of looking more in depth at the star formation rate, star formation history of the galactic center as well. And this is just a kind of teaser. This is some data from Adam Ginsberg. This is what the the brick looks like with JWST. So you see all this beautiful structure, particularly in the outskirts, and there's much more to come from this. We now have a few clouds observed with JWST. I'll stop there. Sorry for running over. Yeah, and thank you very much for your time.
I have a question and a curiosity. How many tiles, JWST tiles, do you need to cover the entire region?
Ooh, what is the number? That's a good question.
But it's 120 roughly.
Yeah.
Wow, okay.
This is not going out far from the galactic plane. This is basically 2 tiles above.
And very short exposure by huge overheads.
Well, our main enemy is saturation, actually.
Yeah.
But we keep the program is less than 150 hours. So it's
Okay, fair.
considering
Interesting.
that, for example, you have at least 100 persons strongly interested in these data, 150 or 140-ish hours.
Do you plan also different epochs or all at once?
That would be fantastic.
Because if you redid this 5 years or 10 years later, you would have the proper motions for about 10 million stars.
Yeah.
Okay, now the question.
Can I just say something just before? 'Cause there's a point that I forgot to make on this. Both of these things are open to the community. So if this is something that you are interested in, you can get involved. You know, so if you are interested, you can talk to myself, you can talk to Rainer, you can also send an email to Steve as well, and we'd be happy to have you involved if it's something that you are interested in getting involved in.
Now the question. It's about the star formation history, or if there is like this cycle of star formation. It has been seen in other galaxies, right? The circumnuclear ring, the cluster have ages between 40 million years and 1 million years, but the cluster are all there, still in these circumnuclear rings. Why in our Milky Way, if there is a phase of a bursty phase, let's say, how long that does it last? Why we don't see cluster older than a few million years?
Yeah, go for it, Rainer, yeah. I mean, yeah.
So it's just what is different? I mean, why this cluster in the Milky Way are not visible, or is the burst very short? And I don't know.
It's complicated, is the answer. But I think on the one hand, it's related. I would say it's related to 3 things. First of all, extinction. I mean, Ignacio told us yesterday that these things are incredibly hard to find at only 4 or 6 kiloparsecs. The galactic center is 8 kiloparsec, has extinction of 30 to 100 AV. The other thing is perspective. We're in the plane, which is kind of the same thing. Then it's the colors. So I think actually that these rings, we only see them in certain colors nicely. And finally, and this is true, this is kind of confusing because in principle, in the inner 100 parsec, we would expect star clusters to dissolve, even if there are 10,000 solar masses, they would dissolve in 5 to 10 million years below the background density. Yeah. So this is why we're actually doing this. My student back there, Alvaro, is looking for them in proper motions. But I mean, if the thing is older than 10 million years, it's dissolved in the galactic center, 10 to 20 million years. We don't know, but that's kind of what estimates from Diederik Krausen give us, more or less. And there was also Simon Portegues Suartez's simulation. So just dissolves. It's dense and it shocks. How massive is this brick? 10 to the 6?
10 to the 5.
Yeah.
10 to the 5 solar masses.
Yeah. But you encounter, so any star cluster encounters this on its orbit. Its orbital timescale is just a few million years.
Yeah. The brick actually has a kind of a cavity that you see, that we see in kind of the radio as well, kind of what you might expect if feedback was actually impacting on the cloud. And we did everything we possibly could to try and find a star cluster there, and the kind of conclusion was there. So the mass that you would derive purely from kind of the kinematic analysis and the flux in the radio and things was about 10 to the 3, a few 10 to the 3 solar masses. You could hide that easily in the galactic center.
I mean, actually, in one of the first images that Johnny brought up, you saw it Spitzer, and if you just look at the Arches cluster, it's fly shit on there. It's 150 OB stars. It's like 3 or 4 pixels at this angle. This is like, you couldn't even find Arches on here, which is one of the most massive clusters in the galaxy. If you point to it, there's nothing to see. And the other thing, because I think that most of these beautiful rings that we see, I'm not sure though, but I suspect they have much bigger angular scales than what we have here.
Yeah.
They're more rather at the kiloparsec scale or so, resonances.
Yeah, this is what I was going to say. It's places like 253 where you're forming lots of protoclusters. You know, you're talking about forming 10 to the 5 solar mass clusters, right?
So
It's just
must be more gas.
it's an order of magnitude.
No,
yeah.
it's okay. I shut up.
Thank you very much. So I'm a bit confused because you have showed the plot and the CMZ sort of, you know, being below the expected star formation rate. And then now, like in this talk, like there's now this sort of, you've given this explanation for why in the CMZ the star formation rate is lower. There's this, there are mechanisms to explain that. So I guess what I wonder now is that I don't know from what sort of surveys or results these galaxies have been taken from, but are there examples of other, you know, similar regions, similar surface densities, and with a lower star formation rate than expected in other galaxies that just aren't on this plot?
It's a great question. So some of these blue points up here, so right, first of all, the scatter in this plot. There's kind of two things here, right? There's the expectation that once gas reaches 10 to the 4 particles per cc, it's going to collapse and form stars. That doesn't apply, right? That's kind of what I've been talking about. There's nothing wrong with the plot, right? This is what the data is telling us, right? My point is that the Milky Way probably, its central molecular zone, probably doesn't stay at this location. It probably will move around. You think about it as a kind of an evolutionary thing. So for a good example of that was when I talked about M83, the center of M83. So basically it would be the same location, it would just be up here, right? So in terms of that. There are not great samples of extragalactic CMZs. These are extragalactic CMZs, but I would say they're kind of, the resolution here is still kind of killing us. I think I don't think we're necessarily looking at the precise same thing that we are in our own Milky Way, and you're incorporating larger scales. What we're trying to do now is go to higher resolution. So there's like a handful of, we're now at a point with ALMA in extragalactic CMZs where we were with single dish telescopes 10 years ago in our own, right? So we're getting down to a couple of parsec scale resolution in nearby galaxies, very nearby galaxies. So what we're trying to do now is, so for example, FANGS has an extension where we're looking at a nearby galaxy central molecular zones where we're getting down to sort of 10, 20 parsec scale resolution, obviously depending on the distance of the galaxy. And once we have those things, we'll be able to have, there'll be more data points in here. But you're precisely right, like we need more information and more surveys of extragalactic CMZs to kind of look at.
Of the galaxies that are close enough for a CMZ to be resolved, what fraction, maybe you mentioned already, what fraction have them?
What fraction of galaxies have central molecular zones that look like ours? Is that?
No, more so just more generally, of the galaxies that are close enough for a CMZ to be resolved, in what fraction do you observe one?
I'd have to take another look at Sophia's paper. That's probably the first paper that's trying to look at this systematically. There are other papers older looking at kind of different wavelengths, but certainly looking at the molecular gas. The only statistic that I remember specifically is that 60% of the barred spirals in the FANG CMZ have central rings. I think over the full sample, or within unbarred galaxies, I think it's maybe like 25%. Something like that, but yeah, I would have to take another, I can point you in the direction of Sophia's paper, actually. That's probably the quickest way.
And maybe final question in the interest of having coffee.
Also, Mirka will join us remotely, so we shouldn't let her waiting too long.
Hey, just wanted to add a small question to the previous one. Did anyone try to put on with relation of post-starburst galaxies? Because I don't know if we are talking about that with zone had an activity in the past, and now that's why we're seeing it's a bit under the plot. I mean, if you follow the logic, it seems like post-starburst galaxies might also like
Sit
below.
I don't know that for sure in a systematic way, Mark. Not to put you on the spot, but post-starburst galaxies on Schmidt-Kennicut Gauss-Solomon relations, has anyone attempted to do that in a systematic way?
Not that I know of.
Yeah. Okay. Yeah. Yeah. How would you?
I think if they're post-starburst, they tend to be pretty devoid of gas.
Yeah.
All right. In that case, let's thank Johnny again and let's have some coffee.